Okay, so in this session, we are going to discuss about time reversal filtering, which is a way to implement zero phase filters. It's a non-causal filtering, which means we cannot use it in real time. So we have to use it only for offline applications. Let's start with a basic definition of Z transform. So when capital XZ is the Z transform of X of n, then we know for X of minus n, the Z transform is 1 upon Z, X of 1 upon Z, right? So this is the basic result which we will be using to implement time reversal filtering. So the purpose is that 1 upon Z brings the poles inside the unit circle, right? Why was our system unstable? Because the poles were outside the unit circle. So we will be using this property to bring the poles inside the unit circle by by reversing 1 upon Z, reversing Z. This will make the system stable and we can implement it, right? Okay, so let's see any general H of Z. From this plot, you can tell that there are 4 poles, A1, A2, B1, B2. A1, A2 are inside, B1, B2 are outside. So my H of Z is basically this form, right? 1 upon 1 minus A1Z for the A1 pole, similarly for A2 pole, B2 pole, and B1 pole, okay? Now we break it up into 2 parts. Now this H of Z is not implementable because of B1 and B2 poles, which are outside the unit circle. So let's break this HC into 2 parts such that one part has poles, all the poles inside the unit circle. The other part has all the poles outside the unit circle, right? Okay, so this is how it comes out. My H of Z is now my H of Z is simply 1 upon 1 minus A1Z inverse, 1 minus A2Z inverse. This is stable, right? This is stable because both the poles are inside the unit circle. As you can see in the figure, A1 and A2 are inside the unit circle. Now, the other part is 1 upon 1 minus B1Z inverse, 1 minus B2Z inverse. This part is unstable because both the poles are outside. But now if I implement H2 of Z inverse, which means I replace my Z inverse, I replace my Z inverse with Z, then what happens? All the poles come inside, right? Where is this term 0? This term is 0 when Z is equal to 1 upon B1. This term is 0 when Z is equal to 1 upon B2, right? That's the meaning of pole. The denominator is 0. So now the poles are 1 upon B1 and 1 upon B2. So the poles have come from outside the unit circle to inside the unit circle. Okay. Now, what happens then? So H of Z is equal to H1 of Z and H2 of Z inverse, right? My H1 of Z is stable, H2 of Z is stable, but I have to implement something of this form. We can implement HZ as a cascade of H1Z and H2Z, but how to implement H2Z inverse, because that is not stable. So we must use H2 of Z to implement H2 of Z inverse, right? We must use H2 of Z because that is the stable thing. Okay, so now here we will use the time reversal property. How? Simply I know H2 of Z is stable. Given any xn, I can estimate my y of n simply by convolution, right? So let's write the Z transforms. X of n will have a Z transform X of Z, and y of n will have a Z transform of H2Z multiplied with X of Z, right? Now what I do is I add a time reversal, which means it becomes y of minus n. What is y of minus n? It is H2 of Z inverse and X of Z inverse, right? Because of simply the time reversal property. But we need H2 of Z inverse into X of Z. So this part, H2 of Z inverse, this is a good thing, right? This is what we need. But XZ inverse is not what I need. I need X of Z. That is why we add time reversal at the input also, so that I reverse my xz in the beginning, and so that now when I reverse it, it is in the right form. So I have added a time reversal filtering here, so that my x of n becomes x of z. So this becomes x of minus n. So this becomes x of z inverse, right? So then this becomes h, again here also we get x of z inverse, and here also I get x of z inverse, right? And this cancels out the inverses. So what I get is x h2z inverse times x of z. This is what I wanted, right? So overall what I get, overall is I have my xn, I pass it through h1 of z. This is a stable filter, so we can implement it. And then I do a time reversal. So I get, this is what I get. Now I apply h2 of z, so that I get h2 of z into h1z inverse xz inverse. Now I again apply a time reversal. So I get h2z inverse h1z times x of z. This is what I wanted, right? This is what is equal to my h of z times x of z, which I originally wanted, right? Okay, h of z times x of z. Something like that. Okay. So this is an important result. We'll be saving this result. Means this is an important way to implement uh, unstable systems. Okay. Now time reversal filtering for H hook Z. I think this is very obvious. Simply H2 is same as H1, right? So the same thing can be applied here. This is time reversal filtering for H hook Z. And now some practice problems. Implement HZ, find HZ for implementing a zero phase filter if H e to the power j omega mod whole square is equal to this, right? Um, you know how to do it because this is a zero phase transfer function, zero phase filter, and you know how to break it into two parts. One part which has all the poles inside the unit circle, other part which has all the poles uh, outside the unit circle, and then you reverse that 1 upon z, and that's how you implement. Okay. Now, can you also find the LCCDE that can be used for time reversal filtering? So basically, you have your h of z. H of z will have an LCCDE which is stable, and you can implement. Similarly, the other part, h of z inverse, will also have an LCCDE that is stable and can be implemented, right? Means the counterpart. Um, Now we have to just implement the same filters what we have discussed in the previous slide using LCCD, which is very simple thing. Now, can you implement this in Python? Yes, why not? Right? Okay. So the slight catch here, okay, which is cos of omega, you can write it as e to the power j omega plus e to the minus j omega divided by 2. And when you convert it into a z transform, it becomes z plus z inverse divided by 2, right? So that is all about time reversal filtering for implementing zero phase filters. Thank you.